Hi, linear algebra students. This is the second and last example you have to look in the LU Factorization section 2.5. And it's an example in which we are given LU Factorization. Actually, we're not really given it. We found it in class. Okay, we found in class that this matrix B has this LU Factorization. So this is the matrix L. And this is the matrix U, okay? And what we want to do is to use that factorization to solve Bx equals B for this vector B right here. Okay, so what I want you to remember here, and we've done a similar problem in class, slightly easier though, is that we're basically solving two systems instead of one per matrix in the factorization. So the first step is to solve the system Ly equals B. So Ly equals B. So in other words, okay, so we put the matrix L, which is like 1, 0, 0, then negative 3 half, 1, 0, negative 1 half, 3, 1. Okay, so this is the matrix L. And we augment it with the vector B. Okay, so just for the sake of color coding a little bit, I'll do it in orange, this one. We put this vector B. So 10, negative 15, negative 5. Okay? And then we're row reducing. Okay? Now, I want to mention here that, yes, you're having fractions. Okay? And it's tempting because of what I said to you, because of the way I taught you. It's tempting to just scale them up by 2. Okay? But actually, since the matrix is already like unit lower triangular, it's actually simple to row reduce. So you can take the risk of making row operations that that involve these fractions. So for example, you're going to do row 2 becomes row 2 plus 3 half of row 1. Like that's what I mean. And row 3 becomes row 3 plus half of row 1. Okay, so from there, and I'll oh no, I'll continue the color code on L, I think. Oh no, I'll drop it. So 1, 0, 0. Then we're getting 0, 1, 0. Okay, here. Before I do anything else, let's copy the 10 here because that's the one I'm using. So 3 half of 10 is 15. So in this case, we're lucky. We're ending up with 0. And here we're having 0, 0. And then, oh, okay, well, oh, shoot, this is a 3. Okay, I have to be careful. So again, here we end up quite lucky. 1 half of 10 is 5. So 5 plus 5, 0. Okay, so we end up with that. Then afterwards, obviously, we need to do this row operation of like, so the next one is going to be row 3 becomes row 3 minus 3 row 2. Whoops. Okay. And then obviously we get our solutions 1, 0, 0, 10, 0, 1, 0, and then 0. And then finally we get 0, 0, and 1 with 0. All right. So from there, I will color code the y because we will use it in the next step. So as you can see, the vector y, so the solution to this matrix equation will be the vector 10, 0, 0. So the first row reduction is done. We solved for the first system. So now we're going to the second system. The second system is then to replace this y inside of the ux equals y. So we're solving the system ux is equal to y. So remember, the idea is that first multiplying u with x will give y. then multiplying y with L will give B. So we will have the solution of the composite system. So from there, so now we take U. So U is going to be slightly harder to row reduce than L, simply because we will have more scaling operations to do. But even then, not much more, because the only thing we need, as you can see, is the backward phase. So there. And then we augmented not with the B, but with the Y that we found in the previous step. So then 0, 10, 0, 0. There we go. So, all right. We put this to reduced row echelon form. So we're going to go with, as I can see, we have our two pivots here. So we need to remove that -2. So row 1 becomes row 1 plus row 2. Okay, so that will become 0, 0. Yeah, I'm going to keep it at that, actually. I could have scaled down the second row, but I think it would have been working at cross purpose, because then I'm going to scale both rows at the same time. So we're going to have -2, -6, 0, and 8. And then 10 right here. So now I need to erase the top, like the very, very top. And then we're continuing this, but the only thing we're really doing is from there we do row 1 is half of row 1, and row 2 is half of row 2. So it gives us this matrix 1, -3, 0, 4, augmented with 5. So 0, 0, 1, 2, augmented with 0, and 0, 0, 0, 0, augmented with 0. Okay, so from there we're good. So our final result, right? So this is the vector x, okay? It's the solution to ux equals y, but I want to remind you here that it's also the solution of the composite system. In other words, it's your final answer. It's what you're looking for. So you read this and you're like, okay, I have two free variables here, okay? And so let's read the basic, let's read first the variable x1. So we're gonna have like s and t. Oh, actually, that's it. We're gonna have like a particular solution, which is gonna have 4 columns, plus s times a vector of 4 columns, plus t times a vector of 4 columns. So they all have 4 columns, obviously. So we read the first row for the first basic variable. So I'm actually gonna color code a little bit. So here we have 5 plus 3s minus 4t, okay? And then be careful, because the second variable is a free variable. Actually, yeah, I think I'm going to color code each of the variables. So the second variable is a free variable, which means that we simply have 0, 1, 0. Then for the third variable, right? So you need to read where the pivot is. Then you read the second row, in which you get 0, no s, so 0, and -2t. Oh, I made my vectors big, no worries about it. And then finally, because you have this is a free variable, so let's actually put the pivot in a box, because I want to have like a nice setup. So since the fourth is a free variable and it's the corresponding to the free variable of t, there you are. This is your solution. And just to make my vectors prettier, here goes. So that's it. This is your final answer. All right, I hope this helps. See you in the next video.